Hello, my name is Elena Varghese, and this is my Physics 2211 lab report video. This lab explores the motion of an object being thrown, and I will present my observations, computational model, and compare both while discussing key assumptions. So the purpose of this lab is to observe and measure the position of an object as it falls from rest from a height. I'll be comparing this motion using two computational models. One considers drag force and the other does not. So, some fundamental physics principles that I will be using. The first one is Newton's second law, additionally known as the velocity update formula, which describes the change in velocity when a constant net force acts upon it. Another important formula to this lab is the position update formula, which updates an object's position based on its average velocity and change in time. Additionally, there is the gravitational force, but near the Earth's surface. So, gravity is 9.8 meters per second squared and is in the negative direction because the object's going downwards in the negative y direction. And then, due to air particles in the atmosphere, there is also drag force acting upon the object. So, drag force points in the opposite direction of the force due to gravity. And in this experiment, drag force points upwards. So, some key assumptions: gravity and drag are the only two forces acting upon the system. Another one is that the ball of paper has an initial velocity of 0 meters per second because the ball is starting from rest, and all tracker markings are at the exact center of the object. Um, uh, yeah. So, in this experiment, the system is the ball of paper, and the surroundings are everything else. So, here is my tracker analysis. So data collected from my tracker analysis. There are 0.067 seconds per frame, and my observation of start time is 0.133 seconds. My initial position is stated here, and my object's initial velocity is 0 meters per second, as I said before, because it's starting from rest. So some potential errors that I may be facing are measurement inaccuracies due to rounding errors. Additionally, when using the tracker for each frame, placing the center of mass at different places for might affect the motion being tracked, and additionally outside forces like the AC blowing onto the ball will affect the motion of it. So for my glow script code, here are the initial conditions. I have my system's mass stated there, and then I have my initial conditions of position and velocity, and then my time, the delta t, and gravity. And then on the right, it shows for if there was drag. The proportionality constant would not be zero. If it were to be zero, there's no drag. So for my no drag, here are the equations that I'm using. I'm using Newton's second law, additionally known as the momentum principle. And then I have my position update formula. And additionally, F net is equal to the force due to gravity, which is stated here. So for my computational model for the no drag, this is my iteration. So my max time is 0.7, so that's why I just go up till that point, and then I have F net. Uh, F net. My net force is it's just gravity, so the gravitational force. So I just have 0, negative, mg, and 0, and then I have my momentum principle, velocity update, and position update, and updating the time. And then for drag, my net force is calculated differently. I have gravity, which is 0, negative mg, 0, and then I calculated my the magnitude of velocity because the equation for F drag is stated here. Negative b, and then it is the magnitude of velocity that is squared, and then the direction of velocity. And then for F net is the sum of gravity and drag, and then I have a momentum principle, velocity update, position update, and time. And then for my computational model, here are the arrows that I have. I have my gravitational arrows position, axis, drag arrow, and velocity arrow. And then here are my glow script results. Here is my position, which is going downwards in a slope, and then my velocity is a constant one going down. And then my tracker results, which is my observed, here's the time, and here's the x direction and the y direction. The x direction is obviously the x direction is obviously increasing because it's moving in the positive x direction, and then y is in a downward direction, is going in the negative y direction and is decreasing because the ball is falling from a height downwards towards the ground. So comparing the observed and predicted motions, here is the observed due to because of my tracker, and then here is my predicted motion due to the glow script, the computational model, and you can see the difference because here there is also a drag force acting on it. This is my no drag. There are a lot of discrepancies. Okay, so for my further questions. So, terminal velocity happens to when a free falling object experiences zero net force. So, do any of my models predict a terminal velocity? So, these are my computational models. This is without drag force, which is going straight down, and this is with drag force, and there's a slope. So, my computational model with the terminal velocity that predicts a terminal velocity would be with the drag force. But so you can see as it slopes down, it reaches towards an asymptote, and when it reaches that asymptote, that is the terminal velocity. This one does not predict that. This one does. The drag force does. Another further question is if my object were to be initially thrown straight up instead of just kind of like thrown or downwards or dropped downwards, how long would it take? The time of the object would be longer if I were to throw it upwards. And here is the code that I would have changed in order to determine that and see that using my computational model. Thank you for listening.